students. So this video here is a continuation of functions, function notation, and evaluating functions. So it's kind of a part 2 to that. So first off, let's just kind of start off by just looking at some different ways that relations can be represented. So we can represent relations algebraically. That's talking about with equations. We can represent relations verbally, with mapping, with ordered pairs, using tables, or graphically. Remember that a relation is where you have a pairing of input values with output values. So again, it's a pairing of a set of inputs, which we call the domain, with a set of output values, which we call the range. And so again, we're going to kind of look at, in this particular video, we're going to look a little bit closer at mapping, and we're also going to look at some things graphically. So let's go ahead on and get into this. So again, let's take a closer look at mapping. First off, some of you may be wondering, okay, what is a mapping, Mr. Starkey? Okay, that's a good question, and I'm glad that you asked. A mapping is something that shows elements from one set, and if we're talking about being from that set, we're talking about that's the input. So it shows elements from one set, so elements from the input that are being assigned to or mapped to another set. And of course, the set that they're being assigned to is that output set. So again, it shows again those elements from one set being mapped to another set, and it uses arrows to do that. So guys, for any particular mapping, if you do not have those two sets labeled, so again, if your sets are unlabeled for any mapping, you can actually determine which set is the input and which set is the output based only on the direction of the arrows. So again, all you got to do is really look at the direction of the arrows, and based on that, you should be able to tell which one is the input and the output. But if not, we'll explain that right here, right now for you. So let's look at this relation, or the mapping of this relation on the left here. So you see here that the arrows are coming from this set here with the letters, and it's going to this set here with the numbers, right? So clearly, we should all know that guys, that the output is the result of plugging in an input, right? So based on the direction of this arrow, it should be fairly simple for you to identify which one of these two sets is the result, right? Because you know where the arrow starts, and you know where the arrow ends, right? Based on the direction of the arrow, correct? That should be common sense to you, right? Yeah. Okay, so clearly it starts here. Again, we're talking about the set here that's on the left side. These two sets on the left side. So it starts here on with the set with the letters, and it ends on the set with the numbers. That means that this set with the numbers is clearly, guys, the output, and the set with these letters here is clearly the input, based on the direction of the arrows. Okay, because again, it results with the output. So you can tell that based on the direction of the arrows. And so for this set that is on the right side here, we should be able to tell which one is the output based on the direction of the arrows, and which one is the input based on the direction of the arrows. Okay, just in case you actually encounter a set or two sets for mapping and they're not labeled, They're not clearly labeled where you can tell that one of them is the input and the output. So if they're not labeled, I'm letting you know how to tell which one is the input, which one is the output, based on the direction of the arrows. So again, this would be the input, and this one here would be the output. Okay. Hopefully that makes sense to you. It should. Okay, so next up, let's look at what makes a mapping a relation versus what makes a mapping a function. So the first thing that we need to realize, guys, is that for any and every type of mapping, pretty much, every type of mapping is going to be a relation. So when you look at these two mappings that I have up here, they're both relations. And again, they're relations because, again, a relation is where you have elements from an input set that are mapped to elements elements of an output set. So again, you've got elements of the input set that are relating to or mapping to the elements of an output set. So they're clearly relations. But again, remember, guys, that what makes a particular relation, what makes that a function also is the fact that it needs to have each element from the input set needs to be assigned to exactly one element from the output set. So in other words, each input needs to have exactly one output. Not more than one, not less than one, exactly one output. And that is what's going to make it a function. So again, let's look at both of these mappings here. So when we look at this mapping here on the left side, so if you look at each element in the input set, and again, you should be able to tell which one is the input, which one is the output based on the direction of the arrows, right? So this one is the input, and this one is the output. So if you look at each element of the input here, so if you look at this -1, it has exactly one output that it's assigned to. Perfect. The 0, exactly one output that it's assigned to. The 1, exactly one element that is assigned to in the output. And the 2, exactly one element that is assigned to in the output. So again, for this set here, for this relation that's on the left side, again, each element of the input set is assigned to exactly one element in the output set. So because of that, this relation here on the left side is a function as well. Alright, so again, it is a function. When we look at this relation on the right side, and again, when we look at the two sets, again, you should be able to identify which one is the input and the output based on the direction of the arrows. So each element in the input, let's look at it. So when we look at the 11, it is assigned to exactly one element in the output, the 8. When we look at the 12, it is assigned to exactly one element in the output. When we look at this 13, it is assigned to, what happened? When we look at that 13, oh snap, it's assigned to 2 elements. The 13, it has 2 elements in the output. Something ain't right there. Something sure enough ain't right there. So, guys, again, this relation on the right side here is not a function because there's at least one element of the input set, and again, that element that we're talking about is 13. So there's at least one element of the input set that is assigned to more than one element of the output set. Alright, so again, this set on the left is a function because, again, each set of the input, each element of the input is only assigned to exactly one element. So next up, we're going to take a little look at ordered pairs, and we're going to look at what makes a set of ordered pairs. So when a relation is written or represented as ordered pairs, what makes that relation a function also when it is represented as ordered pairs? What makes ordered pairs a function or not a function? Okay, so let's look at these two relations here. First, let's look at this relation that's on the left side, where we've got these four coordinates, or these four ordered pairs: 3, 9, 5, -2, 8, 2, -8, -2. So just to give us a better look at or a better view at these coordinates, again, we're just going to write these ordered pairs out in a mapping type of form. So again, we're going to rewrite these ordered pairs in a different representation, just to give you a little bit of a different perspective before we explain this. So let's write this out. So we're going to do the inputs, which are clearly the x values, and we're going to do the output set, which is the y values. So let's put these. So for the inputs, we've got 3, we've got 5, we've got 8, and we've got -8. For the output, which are the y values, we've got 9, we've got -2, and we've got 2. Now, I know some of you are saying, okay, there's another -2, so we're going to put, no, we're not going to put that. Okay, so whenever you've got something that just so happens to be written twice, please do not include that number twice when you do this set here. Don't write it twice when you're doing mapping, okay? Because there's no need to do that. All right, and you'll see when we draw the arrows, you'll see why. So again, let's put the arrows there for this. Okay, so based on what we see here with the arrows drawn, and again, guys, it's not necessary for us to necessarily write this as a mapping. However, again, I just wanted to kind of give you this perspective of these ordered pairs. So you can see with the arrows drawn here that again, that this one here is a function, because each particular element of the input set is mapped to or assigned to exactly one element in the output set. So again, you can see that this one here is a function, and again, we're going to look at this set here on the right side, and we're going to do the same thing. We're going to write it as a mapping, and we're going to put the arrows, and then we'll look at that. So again, when we look at this second set of ordered pairs, or at this second relation, when we write it out as a mapping, you can see here that this second set is not a function based on the mapping. So again, if we write it as a mapping, okay, you can see whether or not it's a function or not. But again, how do you tell when you're just looking at the ordered pairs? Because again, you shouldn't have to write it out as a mapping in order to tell whether or not it's a function or not. So how do we tell when we're just looking at the ordered pairs? I'm glad you asked, guys. So when you're looking at ordered pairs, and again, it's not necessary for you to write them as mappings. All you have to do is look at whether or not there are any repeating x values. So again, as you look at the set that's on at the set of ordered pairs on the left side, you notice here that there are no repeating x values for those. Again, you got all unique x values, all different x values. Again, for this set of ordered pairs on the left, you've got the x values 3, 5, 8, and negative 8. They are all unique x values, and because there are no repeating x values, then this is a function. But when you look at the relation, again, it's represented as ordered pairs. So when you look at this set of ordered pairs on the right side, you can clearly see that there are repeating x values. You see it's got a 7 here and another 7 as an x value. That's repeating x values. Guys, that is a big red flag, a little red flag, whatever you want to call it. That's a red flag, folks. And because of those repeating x values, that lets us know that this is not a function. So if it does have repeating x values when you are looking at a set of ordered pairs as a relation, then it is not a function. So again, if you got a set of ordered pairs where some of the x values are exactly the same, or in other words, if you have repeating x values, it is not a function. All right. So, guys, next we're going to look at evaluating functions when we are looking at points on a graph. So, we're going to look at how to evaluate functions when we have points on a graph. All right. So, folks, let's look at this here. Here we've got two different functions. Again, folks, I am not Morpheus, and this is not the Matrix. You will not be able to choose between a red pill and a blue pill. Folks, we are going to swallow both pills, and we're going to look at both functions. Okay? Yeah, we're going to go down both rabbit holes. All right. So, we're going to say that f of x is the function that is graphed in the color red, where you see these discrete and discontinuous, non-connected red coordinate points. Okay, so these red ordered pairs, or these red points, coordinate points here, that is going to be the function f of x. And where you see this continuous and connected graph here, that is graphed in blue, that is going to be g of x. Okay, the function g of x. All right, and so we're going to look at this, and guys, remember that if you are asked to find f of -3, for instance, then you are asked pretty much to figure out what is the function value. And guys, remember, when we say function value, we're asking what is the y value when x equals -3. So, for instance, when we're looking at this one here, and I'm just going to click on that. When we're looking at this one here, you can see I've clicked on it. All right, when we're looking at this one here, f of -3. Again, it is asking you to find the function value, or to find the y value when x equals -3. But guys, you got to look at the right function. Clearly, guys, you can see that these two functions are color coded, and we're talking about the red function that we have called f of x. Okay, so you're going to find the y value when x equals -3 for that red function. So let's look at our graph at the red function. So you guys should remember which axis and which direction the x values go in. The x values are determined left and right, right? So again, when you look from the left to the right, you can see certain x values here. On the right side, we've got these positive x values. On the left side, we've got these negative x values on the left side of the graph. And so we're looking for the x value -3 for this first one. So we should be able to clearly see where that x value negative 3 is. I've got my mouse pointer up there right now, and you should be able to see that that is the x value negative 3, and the particular point, that particular ordered pair or coordinate point that has that x value of negative 3, now I've got my mouse and my pointer on that particular point. And you should see that. That is the point that we're looking at. It has the x value of negative 3. So at that point, which has the x value of negative 3, what is the y value? What is the y value at that point that has the x value negative 3? So, guys, if you're having issues with seeing that, just count it, okay? If you're having trouble with looking at how the graph is labeled, literally just count it from the origin, okay? Because now, if you didn't know before we did one of our previous videos, you should know how to tell what that ordered pair is at this point that I have my mouse pointer on. So again, from the origin, the x value there is negative 1, negative 2, negative 3. We already knew that, right? The y value at that point is 1, 2, 3, 4. The y value, literally all you got to do is count. From the origin, that is left 3, 1, 2, 3, left 3, and up 1, 2, 3, 4. The y value is positive 4 there. So again, what that means is that for this particular one, f of negative 3 is going to have the function value or the y value of 4. So f of negative 3 is equal to 4. Easy, simple, not rocket science. All right, let's do these other ones real quick. F of 5. So again, we're looking at the red function. We're going directly to the x value of 5. So let's count it from the origin. We're going right 5 from the origin. 1, 2, 3, 4, 5. There's only one point, one red dot that has the x value of 5. And that is if we go down 3, right? So that's 1, 2, 3 down at that x value of positive 5. So from the x value positive 5, again, that was right 5 from the origin. The only point is down 3. So that's 1, 2, 3, down. Down 3 means that the y value there is negative 3. So for the point, for that red point that has the x value of positive 5, the y value is negative 3. So therefore, that means that f of 5 is negative 3. Let's look at the next one. Let's look at f of 9. We're still looking at the red graph, at those red dots, those red ordered pairs, those red coordinate points. So f of 9, we're looking at the x value 9. Let's count that from the origin. That means we're going right 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 to the right. There's only one ordered pair, one coordinate point that is at that x value. And we have to go up in order to get to that point. We have to go up how many? 1, 2, 3, 4, 5, 6, 7. Literally, it is counting. So, at the x value 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, the only point at that x value is up. 1, 2, 3, 4, 5, 6, 7. Which means that this value for f of 9, the y value there is 7 at that point. The y value is 7 when the x value is 9 for the red points. Alright, and then the last one, f of negative 5. So again, if we go to that x value, that is 1, 2, 3, 4, negative 5, right? We're going to the left. 1, 2, 3, 4, 5. Negative 5. The only red coordinate point at that x value of negative 5 is where we go down. Down how many? Let's count it. 1, 2, 3. So if we had to go down 3 at that x value of negative 5, that means that the y value there is negative 3. So the y value at that x value is negative 3. So we've evaluated we've evaluated those particular ones there. Alright, so let's go ahead on and do the blue function, g of x. Alright, now, guys, oops, and sorry, I didn't write those as g of x. Give me a moment here. Ooh-wee, that was quick. Was that a moment? Alright, so, let's see here. Again, guys, we're looking at g of x. Now, guys, they will not always color code your functions. So please make sure that you read the directions very carefully. Because, again, I'm being very, very detailed here and giving you a color coordination here. But not everybody is going to be that nice to you. But, again, we're looking at the blue graph. The one that they've told you is g of x. And so... let's see here. So if we're asked to find g of negative 3, again, we're looking at the blue graph. So we go to that x value of negative 3. So again, x values, we go left to right. So from the origin, negative 3 as the x value means we go left 3. 1, 2, 3 to the left. So my mouse pointer is there at the x value of negative 3. The only point on that blue graph that is at this x value negative 3 means that we have to go up, right? The only point on that blue graph is up. Up how many? It is up, let's count it. 1, 2, 3. It's up 3. So what that means is that at that particular x value, at the x value negative 3, the y value is up 3, which means the y value is positive 3. Haha. The y value is positive 3. Alright, let's do the next one. So for this next one here, we are looking for g of negative 5. So we go to the x value of negative 5. So from the origin, let's count it. Let's go left 5. 1, 2, 3, 4, 5 to the left. The only place on this graph, or the only way for us to go, as far as with the blue graph, is for us to go up in order to reach a point that's actually at this x value of negative 5. We have to go up, okay, to get to the blue graph. So it's up how many? Let's count it. 1, 2, 3. Oh snap! This one's also up 3. So guess what? That means that the y value at this particular x value is 3. That's not 3. Let's try that again. 3. Next, we're asked to find g of 3. So again, we go to that x value. So let's do it from the origin. If the x value is 3, we go right 3. That is 1, 2, 3 to the right. The only place on that blue graph, g of x, we have to go down in order to get to that blue graph. So down how many? Let's count it. 1, 2, 3. We go down 3. That means that the y value at this particular x value is negative 3, because we had to go down 3 at this x value. So let's do that. So the y value there at this x value is negative 3. Next, we're asked to find g of negative 8. So let's go to that x value, negative 8. Let's do it from the origin. Let's go left 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay? So in order for us to get to our blue graph, wait a minute. The blue graph is right there. We don't have to go up or down. So what does that mean? If we don't have to go up or down, that means that the y value at this particular x value is 0. Right? So the x value here is negative 8, and the y value at this x value is 0, because we didn't have to go up or down in order to get to that blue graph. So for this one, the y value here at this x value is 0. I hope that makes sense to you guys. So next, we are going to look at how to evaluate a function. We're going to look at how to evaluate or how to find the output. we're going to look at how to evaluate, how to find the input of a function when we are given the output. So we've done something in a previous video on how to evaluate and in other words, how to find an output when we're given an input, because I mean that's the way you would normally do it anyway. But we're going to look at what to do when you are given an output and asked to sort of do the reverse thing. When you're given an output, we're going to ask you to find the input here. Okay? Alright, so you might be thinking here, okay, Mr. Starkey, I've never done this before. Well, that's why we're talking about it. So, you know, your question might be, well, how do we do that, Mr. Starkey? I mean, what are we supposed to do exactly? That's a good question, y'all. I'm glad you asked. Let's talk about that. First off, you need to substitute the given value into the equation. Then, what you gonna do? You're gonna solve that equation for the missing value that they're asking you to find. Ha! Look at that. Alright, so let's look at this example. Here we've got it saying, if g of x is equal to negative 3x squared minus 8x plus 2, then find x when g of x equals 6. Pause. Some of y'all might be thinking, really, Mr. Starkey? Did you really just give us a quadratic equation? Why didn't you just give us a linear equation? It would be so much easier with a linear equation. You know what? I could have written down an example with a linear equation. I could have made it something like 3x minus 2. I mean, y'all know how to. I mean, let me just kind of go through that real quick, right? So if that was the equation instead of what I've given you, and I'm going to erase this afterwards, you know, just to show you how easy that would be, right? I mean, I mean, if I was asking you about this and g of x was 3x minus 2, right? All you would have to do is literally substitute that g of x, substitute that value 6 in the place of g of x, right? 6 equals this, look at that, equals this right here. And I'm writing it sloppy because I'm going to erase it anyway. And look at that. Look how easy that would be to solve it, right? You would add 2, that would be 8, and then you would have to divide by 3, and so x would be 8/3, right? And I'm about to erase all of this. Right? Look how easy that would be. Easy peasy. So we're gonna make it harder by making it a quadratic equation, because I'd rather give you an example where I know that is something that you might see like on your final exam, that state given exam, right? So we're gonna look at something like that. So you can't say that, oh, Mr. Starkey, you ain't show me nothing that was that hard like this. Yes, I did. So again, we're gonna look at this example, and we're going to substitute the given value there. So we're given the fact that g of x equals 6. Okay, and they want us to find the x value when g of x equals 6. So if they're telling us that g of x equals 6 here, clearly, guys, we need to substitute 6. We need to replace the g of x with 6, right? So instead of us rewriting this and still having g of x written there, they've told us that g of x equals 6. So what are we going to put in place of g of x? I'm glad you guys know, right? 6. There we go. So we got 6 equals negative 3x squared minus 8x plus 2. So guys, there are some different ways that we talked about how to solve this. We've talked about how to solve it using the quadratic formula. We talked about how to solve it by factoring. We talked about how to solve it quadratics by completing the square. We talked about how to solve quadratics by graphing. It's really up to you as far as which way you choose. As far as in this video, I'm just going to show you. I'm going to solve it by completing. Sorry, I'm going to solve it by factoring. In this particular video, I'm not going to complete the square because we'd have to divide each term by -3, which means we'd have quite some we'd have some fractions in there that y'all probably wouldn't want to deal with. And probably the easiest way to solve it would be to use the quadratic formula for some people, or if you knew what you were doing, you might be able to solve it by graphing as well. But I'd want to make sure that you knew exactly what you were doing first with that. All right. So again, in this particular video, I'm gonna solve this by factoring, and then I might just show you I guess the easiest way to do it as well, which would be first off, if you set this equation equal to 0, So if you were going to try to solve this by factoring, you would need to get it set equal to 0 first. You'd also need to get this equation set equal to 0 if you were going to use the quadratic formula. So I'm just letting you know. Again, if you were going to solve by factoring, you'd get the equation set equal to 0. If you were going to use the quadratic formula to solve, you'd set the equation equal to 0. And I'm also going to let you know, if you were going to try to solve this by graphing it, which I'm letting you know is probably the easiest way, you'd also want to get this equation set equal to 0 first. All right, but again, I'm going to go ahead on and do this by factoring here. Alright, so guys, remember that not every type of expression is factorable, but again, I happen to know that this one is factorable. So let's solve it by factoring. Again, the first thing is we want to set it equal to 0, set your equation equal to 0. So the first step there is subtracting 6 on both sides, so it cancels out on the left side here, and we're left with 0 equals that expression. Alright, so next what we want to do is multiply the a value times the c value. Alright, so again, we identify here that the a value is -3, because again, this expression is in the form, in standard form, which is ax squared plus bx plus c. So a is -3, c equals -4, and when we multiply those two values together, a times c, which is -3 times -4, we wind up getting that a times c is 12. So we multiply those a times c together, and now we need to find two factors of that number that will also add to give us the b value. And again, guys, we know here that the b value is -8. So we want to find two factors of 12 that add to -8. So guys, again, you need to know your multiplication factors. It's not too late for you to learn them. Yes, it was an elementary school thing, but it's not too late for you. You've got the mental capacity. I believe in you. If you don't already know your multiplication tables. Alright, so 12, again, factors of 12 are 1 and 12, 2 and 6, and 3 and 4. The factors here that would add to 8 are 2 and 6. And in order for them to add to -8, they would have to be -2 and -6. Alright, so we've identified those two factors of AC. We've identified those two factors of 12 that add to -8. Now what we need to do is rewrite the middle linear term, -8x, in this example. We need to rewrite that using those two factors. Alright, so let's do that. We've still got the same equation, -3x squared minus 8x minus 4, and we're going to rewrite this middle term. And actually, we were looking at -8x, right? We're going to rewrite this middle term here using both of those factors. Going to rewrite it. We're going to split it up. Alright, so when we split this up, we've got -3x squared still, and this time it's gonna say -2x and negative 6x. So we've split that up, and now instead of it just saying negative 8x, it says negative 2x minus 6x, because technically those are equivalent, right? Negative 8x is the exact same thing as negative 2x minus 6x. Yes? Yes, right? So we can do that. So we have taken that middle linear term, negative 8x, and we have rewritten it using those two factors. Next, what we want to do is we want to actually group our terms. Group the first two terms together, group the second two terms together using parentheses, right? Because we are factoring by grouping. All right, so let's do that grouping where we group the first two terms and the last two terms together using parentheses. So we put negative 3x squared minus 2x together in parentheses, and we group these last two together using parentheses. Negative 6x and the minus 4. Group those together. All right, so next, now that we've got these grouped, again, since we're solving by factoring and we're factoring by grouping, we want to go ahead on and factor out the GCF from each group. Okay, so when we look at the GCFs from both groups, the greatest common factor from this first group is x. Okay, and the greatest common factor from this second group here is 2. So when we factor those GCFs out, it's going to look like this. When we factor out the x, what's going to be left over from that first group? So if we factor out an x there, there'll be a negative 3 and the x still left over. And, well, at least from that first term. And then from the second term, if we take out an x, there'll still be a minus 2 left over. Okay? So, and then from the second group, if we factor out that GCF or take out that 2, we're going to wind up having, from the first term in that second group, we're going to wind up having negative 3x left over. And from the second term in that second group, we'll have minus 2 left over. So again, you should notice here, again, that we do have the same factor that shows up there. So we've got the same factor, and you should notice that, and we've also got the GCFs. So we're going to write out our two factors here. One of the factors is going to come directly from the GCFs, x and 2. The other factor is going to be that same factor that we've got right here, that negative 3x minus 2. Okay, so let's do that. Let's write out our factors in that form where the first factor is coming from the GCFs and the second factor is coming from that same factor that we see. Let's go ahead on and do that. So here we've got 0, and if we write out that first factor, that's going to be x plus 2. And then if we write out the second factor, that's going to be negative 3x minus 2. And from there, guys, we need to go ahead on and use the zero product property. And that means that we need to set each factor here equal to 0. Set each factor equal to 0 and solve, because we're solving by factoring here. Alright, so let's do that. Let's set each factor equal to 0 and solve. So here we're going to have x plus 2 equals 0. And we're going to have negative 3x minus 2 equals 0. And we're going to solve each equation. And so when we solve this first equation, we subtract 2 on both sides. Minus 2 minus 2. And clearly here x is going to be equal to negative 2. And then, of course, with this equation here on the right side, if we add 2 to both sides, add 2, we wind up having negative 3x equals 2. And then you're going to have to divide both sides by negative 3 and when we divide both sides by negative 3, we'd wind up having 2 divided by negative 3, which is negative 2/3. So these are our 2 answers here. Yes, there are 2 answers because we did a quadratic equation, and we know that when we're dealing with quadratics, a lot of times there are 2 answers. Alright, so that was us solving this using or solving it by factoring. And again, we were finding the x values or x values when g of x was equal to negative 6. So again, guys, remember what we did was first we substituted that given value into the equation. You see, we replaced the g of x with the 6, and then what we did was we solved the equation for the missing value. It's not my fault that we were solving a quadratic. Okay, but again, it's just reinforcing what we've been talking about during that last unit with solving quadratic equations. So, hey, again, we have found the x values when the y value was equal to negative 6. So that is what it's asking for here. We have found these x values when the y value was equal to negative 6. Probably an easier way for you to do a problem like this, like I said, would be solving it or doing it by graphing. But again, if you wanted to do this by graphing, where you evaluated this when the g of x was equal to 6, again, guys, after you substituted that given value into the equation, you would need to make sure that you have set the equation equal to 0 first. So again, make sure if you're going to try to do this by graphing, which I'm about to show you, that you're using this equation where it is already set equal to 0. So you're using this equation: 0 equals negative 3x squared minus 8x minus 4. Okay, where the equation is set equal to 0 before you try to graph it and solve it by graphing. I'm letting you know this because some people are going to think, oh, well, I found a shortcut, and you're going to forget. Some people, I hope that you don't, because I'm telling you not to, but some people would forget to solve this equation for 0, and they would just write it as 6 equals such and such and such and such, and it wouldn't work with the way that I've shown you how to solve by graphing if you don't set it equal to 0 first. So again, we're going to use Desmos, and I'm going to show you using this equation where we have set it equal to 0, and we're gonna get the exact same solutions that we just now got here: negative 2 and negative 2/3. And we're going to use Desmos graphing calculator. Alright, so remember, guys, with Desmos graphing calculator, it's a website. They've also got an app on any type of phone, Android, also on Apple phones. They've got the app for Desmos graphing calculator, and all you got to do is look for that little green logo with the little graphs up there, and it says Desmos. But anyway, so remember, guys, that that equation that we want to put into Desmos graphing calculator, if you didn't want to do all of this using one of those methods that we had already previously talked about with solving quadratics, if you didn't want to actually do what seemed like a long process, either solving by graphing, solving using the quadratic formula, solving by completing the square, or something like that, if you didn't want to do one of those types of methods and you wanted to try to solve it by graphing, which would probably be the easiest, you need to make sure that the equation was set equal to 0. Again, I'm repeating this to make an emphasis here, guys, because it's important for you to know. If you're going to do it the way that I showed you how to solve by graphing, it would need to be set equal to 0. So again, do not put that 6 equals equation. Do not put this equation where it's equal to 6 into Desmos. Set it equal to 0 and put this equation, the 0 equals negative 3x squared minus 8x minus 4 into Desmos. Or again, put the equation after you have set it equal to 0. 0 equals negative 3x squared negative 3x squared, let's see here, minus 8x, if I'm remembering it right, and then minus 4 here. Okay. Alright, let me just... Okay, so that is that equation there. Let's just make sure that that is the right equation. Okay, okay, so negative 3, negative 8, negative 4. Let's make sure... Negative 3, negative 8, negative 4. Yes. Alright. So that is the right equation, and it's the one where it's equal to 0. It's quadratic. Again, folks, remember we had said that to solve a quadratic equation by graphing, you need to identify the x-intercepts. So, again, folks, you shouldn't find it hard to identify what the x-intercepts are here on this graph. If you know where the x-axis is. Again, if for some reason you're having trouble with identifying where exactly the x-axis is, again, folks, remember I told you that you can put in a second graph here that will kind of show you which one is the x-axis. If for some reason you're having issues with identifying what the x-axis is, and again, the x-axis, another equation for that is y equals 0. Remember, so that line just showed up as a blue line there. That's the x-axis. So the place where that x-axis, that blue line, is actually touching the red graph that we've got here, those are the x-intercepts. So and again, those dots were there even before I put the before I graphed that x-axis up there with the line y equals 0. But again, you can click on these. Remember, solving quadratic equations by graphing. Again, guys, these are the exact same two solutions that we just now found, negative 2 and negative 2/3. Again, of course, they've got negative 2/3 written as a decimal, negative 0.6 repeating. But again, they're the same two answers, negative 2 and negative 6 and negative 0.6 repeating, okay? So again, those were the exact same two answers right here. And that's how you would, again, that's how you would evaluate a function or evaluate the input of a function when you're given the output. That you first got to substitute the given value into the equation and then solve the equation for that missing value. All right. I do hope that this has been helpful to you. And again, I can if you didn't believe me before about what would happen, I think that this equation before we had set it equal to 0, it has said 6 equals negative 3x squared minus 8x minus 2, and it may still say the same thing, or no, plus 2. It might still look the exact same way. Okay, well, Desmos is real good then. I'm sorry, folks. I was wrong. Apparently with Desmos graphing calculator, apparently you won't have to get that equation written at where it's set equal to 0 before you do it here. I'm sorry. I did all of that reiterating. Apparently, yeah, Desmos graphing is real good. Okay, it'll still do it the right way, even if you put it in the way that it originally was. So again, I'm going back. I'm correcting myself. Okay. Again, I thought that Desmos wouldn't do it the right way. I know, but okay, it is though. All right, Desmos is real good. All right. So again, folks, apparently it won't matter whether or not whether or not you got the equation set equal to 0 if you're using the Desmos graphing calculator. But again, you need to remember how it is that we solve these types of equations. How do we solve quadratic equations? By graphing, where you're finding the x-intercepts. Alright, so again, it will still identify those x-intercepts as -2 and -2/3 here. Alright, and so, hey, I do hope that this video has been helpful to you. That's it, folks. Yeah, look at the time. Yeah, alrighty, that's all. Goodbye, good night, have a good one.